Great. Yeah, it's great to be here. Sort of when I sent in the title and abstract, I was perhaps a bit too ambitious. Sort of, it won't be 50-50 service allocation and congestion pricing. Might not even be 85-15. We'll see. Yes, I'll perhaps start with the high-level vision and sort of how I think about a lot of these problems, which is, we like a lot of the talks so far have sort of been under this vein, is that we're definitely in an opportunity to do a lot of equity-focused work in practice right now, right? There's large, granular, often open data or like semi-open data. We have all these modern computational techniques, machine learning, algorithmic fairness literature that have spent a lot of time thinking about all of this recently. And often, if you look at the right places and are willing to talk to people, you have sort of equity-focused practitioners who really sort of both have important decisions to make and actually care. And so there's a lot of opportunity to do good work sort of nowadays in this space. Oops, and I already messed up the clicker. Okay, right, but I think sort of with that opportunity, there's also a challenge that real-world data is often complicated in all sorts of ways that we don't always sort of necessarily think about or incorporate when making decisions. So censoring, distribution shifts, spatial temporal heterogeneity, strategic behavior, all sorts of things, right? So how do we sort of do good work, sort of taking advantage of this opportunity while sort of our data is never going to be as good as we want? And in particular, sort of the framework that I like thinking about a lot of this that sort of I'll give an extended sort of example in the context of service allocation in a little bit is sort of how do sort of just like status quo ground truth realities of existing disparities, both spatially and along socioeconomic lines, sort of how does that connect? And I keep messing up the clicker. Okay, like sort of how does that collect? Sort of how does that connect to the data that we actually end up observing? Sort of what data do you need to make decisions? Is this data sort of available sort of homogeneously throughout the population or heterogeneously or spatially? Is it missing at random or are there patterns for where it's missing? And sort of if this data is, it has patterns in where it's missing or suboptimal, how does that affect your decision making? What sorts of interventions are feasible? And sort of like what sorts of interventions are sort of good to make. And sort of a go-to example that I like making here is, I don't know if sort of how many of y'all remember of sort of in the early days of the COVID vaccine, Stanford Hospital in particular, sort of there was, they had a vaccine allocation algorithm for its doctors, right? So like which doctors would get sort of the vaccine first versus sort of maybe later. And they had an algorithm that sort of, took into account the things that you would want them to take into account. So like age, and so like other health status, vulnerability, and also sort of like where they were sort of in the hospital, right? So like, were they working in the emergency room or the ICU? Were they sort of mostly office job or out clinic? Sort of they tried taking all of this into account and they had an allocation scheme. What ended up happening was basically residents who were the frontline workers for, in the hospital who were working the most hours, were basically all the residents were near the end of the scheme. And it's sort of, there was outrage, there were protests, and they ended up changing it and sort of so on. And if you read the news articles for what they say happened, which, I'll believe, sort of what they blamed it on was the location field for the residents was missing. Residents didn't have a home location because they moved around the hospital in different sort of not in different shifts, but in several week periods and so on. So they just didn't have a home location, and so they didn't have a score for any of the location contribution. When like if you actually look at the fact that they're moving around, they probably should have a higher score, and sort of that sort of missing variable led them to be near the bottom for the most part. Right, and so that's an example of sort of a clearly sort of heterogeneously missing like data aspect is affecting decisions to the point where you're like, okay, should I even use this algorithm in the first place? And my claim is that I think this happens in a whole bunch of places and we need to sort of think about estimation and decision making sort of together. Right, and so today I'm going to spend most of the time talking about our work in understanding and improving government service allocation, and then perhaps near the end, sort of some new work on congestion pricing. Okay, so government service allocation, it's important, right? So the local government, I like to say besides immigration and maybe criminal justice is probably, the local government is probably your biggest interaction sort of with government sort of on a daily basis. And right, so it manages many services. So in New York City, they have about 8,000 miles of streets that they need to manage. So when I say manage, of course, new construction, but also just inspections, fixing potholes, fixing bigger things in potholes, floods, all sorts of things. There's about 700,000 trees lining the streets in New York City. This is not counting trees in parks. So if you count, include the trees in parks, I think it's closer to 1 million. Right, and just all sorts of other things like housing, sanitation, all sorts of work that the city needs to maintain. And if it doesn't maintain it well, sort of perhaps bad things happen. Right, so what are the operational tasks in maintaining these things? Well, first they have to learn, right? You have to know what are the problems that even exist. We don't have perfect 24/7 surveillance in cities, especially if like an indoor housing thing. And so, the city has a learning problem of like, where is there even a pothole or, an exploded fire hydrant or whatever. Once it has, some amount of knowledge of what problems are out there, it needs to solve a daily allocation problem or an hourly allocation problem, what have you, for different types of incidents, which is like, which of them am I going to address right now? Which of them maybe tomorrow? Which is going to go on a stack that like a year from now or whatever. And then in hindsight, so they're making all these decisions in real time, and then in hindsight, an agency sort of deputy commissioner might care about solving an auditing problem, which is like, did we do a good job, right? Is all of these decisions that we were making, are they good under some efficiency, equity, desiderata? And you can define this in many ways as sort of various people have talked about in talks. And okay. So in New York City, and certainly in many cities, both throughout the United States and throughout the world, the primary way that the government does this first step of learning about problems is actually through crowdsourcing systems, where people are telling them, here's what's wrong, right? And so in the United States, they're often called 311 systems, which is a phone number app, Twitter, all sorts of things that you can use to complain to the local government. And so New York City, for example, receives about 3 million service requests a year. The actual number of calls is way bigger. It's like 30 million, but like the subset corresponding to like do something for me is about 3 million. And this is really the primary way that the local government is learning about a whole bunch of problems, right? And this is both emergency, urgent, like the street is flooded, you need to like clear the catch basin, or this like tree has fallen onto the roadway, you should like fix it up immediately. And then also more routine problems, like a tree is about to overgrow onto a power line, or like a smaller pothole or something that maybe you can address down the line. Right, and so here's like, a high level pipeline of what, like the mental model, if you could imagine what's going on, is you have some sort of incident. So here, maybe a tree falls down onto the streets. At some point, hopefully, it generates a report, right? So, for example, just to put some numbers, the forestry subunit of the Department of Park Recreation that we talk a lot with sort of generates about 70 to 100,000, sort of receives about 70 to 100,000 reports a year. The agency needs to decide what to do in response to reports. And so the first step, what they often do is send out an inspector. So this is like a trained, usually someone who has like a master's degree in forestry or something, where they literally go out, they've been trained in this extremely long sort of like tree management planning, like here's how you assess trees. They go out and they like conduct a survey of the problem, and they log it. And they sort of do a risk assessment of what went wrong. And this happens about 2/3 of the time in response to reports. And then about half the time in response to an inspection, the agency actually sends a maintenance crew. And this, this doesn't happen immediately, of course, but at some point, about 1/3 of reports end up like actually having a maintenance crew sent out to fix whatever was wrong. Right? And sort of what we want to do is we want to understand and improve this entire pipeline from sort of estimations. How is the city learning about what's wrong? And then how does that lead to decision making of addressing whatever is wrong? Right? And we care about both efficiency, where you want to do that you want to make sure that the high risk things are done as soon as possible. And you also care about equity, where sort of you don't want high risk things in some places sitting for longer than others, or you don't want define it however you want. You don't want like the total risk days to be inequitable across spatial units or demographics. Okay. And so maybe I can just bring up sort of part of the empirical findings is there are clearly disparities at every stage of the process, right? So what you see here is, and I'll sort of, in the next few slides, I'll talk about how we measured this. But the red part is our estimate of reporting delays. So this is the subset of incidents that like actually sort of were deemed super high priority to like actually fix. Like these are the most urgent things amongst the inspector reports. And the red is our estimate of how long it took for it to be first reported, right? So the super high priority thing in Manhattan, we estimate about 1 day. And in sort of the Bronx, 3 days, and Queens, 6 days. Sort of, for those of you who don't speak New York counties, sort of Manhattan is maybe the main part of New York that you've heard of, or sort of all the business folks and sort of relatively higher wealth. Queens is more of an immigrant and minority population, same as the Bronx. So sort of there's definitely reporting disparities, right? On the order of days, even if you're like conditioning on the same like super high priority urgent incidents. There's further on top of that inspection delays once it was reported, and these can be calculated immediately because like we just know when things were reported and we know when things were inspected, right? So in Manhattan, this incident takes like less than a day to inspect. In Brooklyn, 1, maybe in Queens, 3. And then there's further disparities at the work order stage, right? So in Manhattan, it's so small you don't see it. It's like basically rounds to 0. In Staten Island, about 7 days. In Bronx, 9 days, and so on, right? And so we have sort of in every stage, there's differences. And in some cases, later stages are making up for delays in the earlier stages, right? And in other cases, they're sort of being reinforced. In other cases, sort of you have sort of longer and longer delays in each stage. And so this is sort of what I want to think about, I want to measure, and this is sort of what we want to improve.
How do these account when multiple people report the same thing, but maybe 2 days later the guy says, hey, what's up, and so on? Is always only the first one counted? Or?
Yeah, great question. So duplicate reports are definitely a thing. They happen about 20% of the time. I'm going to talk about why they're actually great because they help in estimating this red thing. And this is sort of looking at unique incidents as labeled by the agency. And then the inspection is from the time of the first report.
Okay. Another quick thing I was wondering, I find it sort of remarkable that the only thing in the beginning is the citizens. Like, is there no mechanism for police officers, hey, look out for things, or other people?
No, yeah. So like sort of so, you can have resident reports through 311. Sort of that's certainly the predominant thing. I'd have to remember what the exact, I think that's like over 90%. You also have things like, exactly, like police officers or some other agency employee is just out on the streets and they can report something that's actually logged in as something different.
That's also if they happen to see something.
Yeah.
There's no dedicated people
exactly.
who goes out the streets for just looking out for things? Or
the agencies also do active inspections on about like, oh, this is embarrassing. I always forget if it's 5 or 20% because it's 1/5 or 1/20. I always forget. And they do active inspections of a subset of the trees every year. And the same thing, the Department of Transportation does active inspections for a subset of roads, and they have, for transportation, it's 20% because they have street ratings about every 5 years. Right, so certainly there's active inspections going on as well, but that's like on the order of like one inspection a year for a subset of things. But it's not like the spatial temporal granularity you would want for like a real-time response system. And there's a lot of people working on sort of sensors to sort of automate more of this, right? So New York City has flood sensors now in a bunch of neighborhoods that just sort of give you like have straight down IR that gives you like every 5 seconds the water level. A lot of people are doing a lot of smart city things to automate this as much as possible, but at the end of the day, there's many millions of things and there's not that many sensors.
Just a quick question. Are the inspection and work orders are centralized in the city level or?
Great question. So that's actually an active sort of debate that they're having, an active sort of plan that they're switching over, I think, on May 1st, where they're centralizing more of the operations. At the moment, they're per borough. At the moment, and I'll talk about this in a little bit, and sort of our work in sort of understanding these budget levels and sort of the policy decisions they're making. And at the moment, they have a budget of inspections per borough that sort of look at that borough. And then some boroughs do spatial splits within that as well. Other sort of boroughs do more centralized within their borough. It sort of depends. But even when they centralize the operations a little bit, ultimately, New York City is a big place. You're still going to have inspectors sitting physically in different locations, and so the things that they end up doing are going to be, they can be cross-dispatch, but the things that they'll end up doing are going to be more localized to where they are anyway. Okay. Oops. Right, so this is essentially what we want to understand and improve. And so in the first part of the talk, that's many minutes in, I'm going to talk about our work and understanding this first part of the pipeline, right? So how do we understand heterogeneous reporting behavior and sort of when an incident generates a report, because that's going to be helpful for the decision-making stage, right? So in the second part, that I'll talk about a little bit, this is more ongoing work, which is how do we understand and make optimal decisions in the presence of heterogeneously missing data and needs, right? So in the context of, we just are maybe going to get fewer reports conditional on the ground truth in one location or delayed reports conditional on the ground truth, right? How do we make decisions? Okay. Right, and maybe I don't need to reemphasize this, but understanding reporting behavior is important because if there's disparities in who reports problems, there's going to be disparities in what work gets done unless you actively counter it. Okay, so we want to understand reporting behavior. We almost immediately run into a statistical problem, which is how do we understand, especially in answer to questions, I just tried to claim to you that the city doesn't really have sufficient other ways to learn about problems, right? That sensors aren't good enough, that active inspections aren't good enough, and so on, right? So given we don't have great external ground truth data, how do we distinguish between underreporting? So an incident happened and wasn't reported, or an incident happened and was reported 2 weeks later, and that the neighborhood just truly having fewer problems.
Do you have a ground truth notion of what an incident is? Because I could imagine one thing is a problem to someone and not a problem to someone else. Or something.
Yeah, that's a great point. So ultimately, what I'm going to call an incident is a report happens that generated a row in a data set that's a row of complaints, and then the agency went in and labeled duplicate complaints. So it said these two complaints are the same incident. And that's what I'm calling an incident. Now, you're right that there's sort of incidents that are unreported that, of course, that we care about and we want to measure. And there's also different people call different, right? We haven't gotten around to studying this, but I want to sort of recruit someone to do this, is sort of people provide more data than just like, hey, something's wrong here, right? They leave free text fields, they like label it as a hazard versus something else, and you can imagine different people having different standards for like, wow, this thing is about to kill someone versus like, hey, please check this out, right? So like totally there's entire other dimensions that we're not considering yet. Okay. Right, so, right, but by definition, we don't observe data on missing reports. And so distinguishing between there were 10 incidents and half were reported and 5 incidents and they were all reported is like not possible with like a naive sort of look on the data. Right, and this is like, this is not unique to this context. This is a fundamental problem called the benchmark problem that happens, in a whole bunch of places that are important. So in policing, if you want to sort of think about inequitable policing, often you need to distinguish between, there were differences in how the police were treating people versus there were differences in underlying sort of populations, sort of population behavior. In healthcare, you want to distinguish between, hey, we truly undertested this population, we should have done a better job, and oh, that population actually has better health. In ecology, where a lot of the statistical techniques were developed in like the 50s to 70s, what they cared about was counting the population of a species or how many species there were and distinguish that from like how hard did I try to like look for this species. Right, and so how does this literature go about doing it? In a lot of settings, especially in this 311 setting, the standard approach is to try to use ground truth data on incident rate, right? So how many incidents of each type, hazards, root issues, tree pruning, and so on, do I expect to see in each neighborhood? So like maybe create some fancy machine learning model. Now, it's questionable how you train that model if you don't have ground truth data. Sort of, this is a hard approach to, I think, do in practice, right? And so like some things people have done in the past is like hire a bunch of students to go out and walk the streets and literally get a snapshot of like, here's how many broken streetlights I've seen, and then go back and look at, okay, how many 311 reports did I get about broken streetlights in this neighborhood, right? So you can like literally go out and like painstakingly collect your ground truth, or you can like construct a bunch of proxies and make a bunch of strong assumptions that maybe someone will believe on sort of, I expect to see similar number of incidents based on the number of trees or their size or their species and so on. What we wanted to do in this work, sort of in these set of papers, is can we measure underreporting without any notion of ground truth or with limited access to ground truth? And then sort of as a second thing is from just the reporting behavior, can you not just recover sort of patterns of reporting, but can you sort of try to recover probabilities of individual unreported events? So like this street right now is flooded or not, even though I never got a report about that street.
For the standard approach, do they do it at just one time point, or is there like?
Yeah, that's a good question. So like, I think grad students are expensive. And so, I think they sort of, the stuff that I've seen is like a collection over a month over, the same set of students go to different neighborhoods over a month and sort of walk the streets and collect it. But yeah, it's not like a continual thing over many years. It's like, I have this set of students, here's my reporting effort right now. Yeah. No, and it definitely works when you can do it, right? It's sort of like the walking approach, if you can.
Just about seasonality with some of this stuff.
Yeah, definitely. Oh, there's absolutely huge seasonality in all of this. So like, you can imagine if like over that month, if now sort of at the tail end of that month versus the beginning of the month, yeah, totally.
So what about just using aerial photography or something? I mean, some things you cannot see, but some things like a flooding or a tree on a road or something, you could probably see by just having a drone flying out once, taking a high-resolution picture or something.
Yeah,
why are these things not on the table of using these?
Yeah, no, I think that's a great question of like, especially with modern computer vision, can you like just solve this, like why do all this fancy statistics? But like, yeah, no, totally. And I think that's a sort of, there's people, including some collaborators of mine who are working sort of in that of like trying to use vision to do that. I think that's a great approach that works for a subset of problems, right? So that works for public, like public street flooding probably will work great. Basement flooding, probably not. Bed bugs, probably not, right? So yeah, no, I'm a huge fan of those approaches when they work. Okay. So, okay, but what we're going to try to do is, can we try to measure underreporting without any notion of ground truth? So in this first project, this is with my PhD student, Jia Liu, and Uma Bandaram, who's at the Department of Parks and Recreation in New York City. Sort of the key idea in this work is, can we leverage the rate of duplicate reports about an incident in order to identify the reporting rate from the fact that it existed? And sort of maybe the high level intuition is that the first report about something tells you it exists. And then the second report onwards tells you something about the reporting rate while it hasn't been sort of fixed. And you need to do you need to be careful about how you do that, because incidents don't just exist forever, right? Like incidents are like, they happen and then they get fixed, and you might not have perfect information on when they get fixed. So like you have to be a little careful about how you use that idea, but essentially that's what we do in this work. And so maybe I'll just like briefly talk through the idea in like 2 more slides with exactly what we mean by the model. So my data generating process is going to be as follows. I'm going to have an incident type theta, and let theta basically encode everything that you observe about the incident. So geography, demographics about that incident, about sort of that location, in specific incident characteristics. So like if you have an inspector report, like this long thing, in New York City, you get the tree ID, so you actually know which tree it was, you know the species, you know the size, like literally everything you might care about the incident. And so we're going to say incidents of a type theta occur according to some process that we don't know. And so let's say an incident occurs at some time. And if this follows some process that we know nothing about. Now, conditional on it having occurred, we're going to say that there's some other Poisson process with some rate lambda of theta that we don't know that causes people to report this incident, that induces incident reports, right? So we have time up here. At some unknown time, the thing happens, and we don't know. We as like the researchers don't know that this thing has happened. Then at some point we observe the first report, and we observe the timestamp associated with that report, but we don't, and we observe some part of the type, maybe not all the type yet, but we observe a timestamp, and that's the first timestamp that we observe, right? And then maybe if we're lucky, we observe a second report. If we're really lucky, maybe a third report of the same incident. We might observe agency actions, right? So maybe we observe the timestamp of the thing being reported, the thing being inspected. Maybe we observe a timestamp of the thing being fixed. And what we care about, what our research question boils down to, is can we estimate this lambda of theta, right? Can we estimate how an incident type sort of relates to its reporting rate, right? And that's exactly the quantity that sort of matters for example, reporting delay, right? So if you like believe an homogeneous Poisson process, then you can immediately look at this parameter, take 1 over it, and that's your average reporting delay, right, in days. And right, and reporting delays matter because they're delays in inspections and getting fixed. And then of course, if it's a low enough reporting rate on average, some incidents of that type may never get reported. And maybe one more comment is, it's not a bad thing if reporting rate differs by type. For some types, right? It's like you want super hazardous things to get reported the second they happen, like cracks on the, like much more minor things. Like if it's reported 2 months later, like it probably wouldn't have been fixed for 2 years anyway, right? So some heterogeneity is totally okay, but what you don't want is heterogeneity based on like socioeconomics or neighborhood, right? So conditional on the rest of the type, you don't want some neighborhoods to have lower reporting rates for the same type of incident.
If it's not a Poisson process, for example, because everybody thinks somebody else is going to report it, and only with some delay people start thinking, oh, nobody else, it's still there, right, and so on, which could be plausibly happening, would that data analysis still somewhat approximately hold, or is it really critical that it's Poisson?
Yeah, that's a good question. So our math doesn't carry through, but sort of we do a bunch of empirical checks when we apply it to the data, and it seems that the method works. But yeah, so essentially, another way to say what we're doing is we're looking at the reporting rate from the first report onwards as an estimate of the reporting rate from the time of the incident to the first report.
Oh, but
right?
In case everybody waits for somebody else to do it, that would be
right. And so yeah, exactly. To the extent that that's not a good assumption, like the method's not going to work. But we do a bunch of checks, and like it's actually surprisingly like. From what we can tell, it's surprisingly homogeneous reporting rates. And then I'll show you, turns out in some contexts, you can do some other checks and and it ends up being certainly like in rank order, pretty accurate. In like calibration, there's some hyperparameters you might need to tune that you can tune, but it ends up being good. Okay, right, and so, what is the the missing species insight is like exactly what I said earlier is like, if someone gave you the time it occurred and someone gave you the time the incident died, then you can do a standard Poisson rate estimation task that you might give an undergrad in operations or a probability, and just say that the reporting rate is approximately the number of reports I observed in this period divided by the time period, right? And then you just do this at scale, and then you're done. The problem, of course, is the whole point is that we don't observe when the incident happened, and we might not observe when the incident died, right? Because often the agency reporting a work order is imperfect. Often someone else fixes it or the incident disappears by the time the agency did the work order. And of course, we never observe when it happened, by how this works. And so the second part of what we have to do that I'm not going to detail is essentially how we nevertheless convert this to a Poisson rate estimation task. You just have to stare at this a little bit longer and figure out how you can get an interval time period within which reporting is still Poisson. Right? But then it's like a standard rate estimation task. We basically end up running a Poisson regression. We do a few other fancy tricks, spatial smoothing, blah, blah, blah. But it's essentially, at the end of the day, reduced to a regression once you process the data correctly. Okay. So now we apply it to New York City data sent to the Department of Forest, Parks and Recreation in New York City. Right, so we're going to look at about 220,000 service requests over a 3-year period. And we get rich covariate. So of course, location, latitude, longitude that we convert to census tract and then look at demographics. Report characteristics, so the category, hazard, sidewalk damage, and so on. The inspector has like an extended report, risk ratings along multiple dimensions, tree condition, and so on. Okay, so the first set of results is like, this is kind of like the validity results. If they didn't look like this, you would think the method was wrong, which is, more urgent things get reported faster, right? So if someone marks it as a hazard, it has a higher reporting rate. If it's like one of the categories that don't matter, so like, please prune this tree, or like there's some issue with like the root is growing into the sidewalk, like that reporting rates are pretty slow. If the tree's in good condition, lower reporting rate. If it's a higher risk, as rated by the inspector, it has a higher reporting rate. Right, and these are like huge on the, for those of you who don't speak in log Poisson coefficients, sort of what this practically means is hazards get reported about 3 to 7 times faster than other incidents, higher risk incidents, of course, and trees in poor, critical and poor condition. And I'll convert this to like days in a second. The second set of results is, however, you also see huge sort of reporting rate disparities just based on neighborhood and demographics of the neighborhood. So here what I did, what we did was we theta is high dimensional. We took out all the incident characteristics and just summed up and just looked at all of the the demographic based characteristics based on each neighborhood and then calculated the score for each neighborhood. And for those of you familiar with New York, this should pretty pop out to you that this is Lower Manhattan, Midtown, Upper West Side all have super high reporting rates. As soon as you start getting into Harlem, Inwood, the Bronx, lower reporting rates, and so you'll immediately see demographic patterns if you look at this. And these are not on quite the same order of hazards to everything else, but if you they're in the same range in terms of they matter. Right, and so let's just
precisely with the table, the graphic you showed early on.
What?
The number of days delay till something gets done.
Yeah.
This reporting, does it align very nicely with that as well?
Well, so that graph was generated from all of this, the reporting delays.
No,
right.
You had the delays included. How long does it take for the city to send an inspector, for example?
Oh, yeah. So I had the 3 stages, right? I had the reporting delay, the inspection delay, and the work order delay.
Right, so, okay.
And so the reporting delay of that plot was generated through this map.
Oh, I see. Okay, good, got it.
And then the inspection delay and the work order delays, you can just read off the data set.
Okay.
Is the population density roughly uniform, or did you
No. So there's huge population density differences. That's certainly the biggest demographic coefficient. This is the plot without population density. Yeah, no, definitely population density is the biggest demographic covariate. I mean, you had a question? Huh? Okay, yeah.
Well, I mean, what I was wondering before is whether it could be that if the inspection and the fixing take so long, whether that could cause a culture among the people to feel less of an urgency to report something, or whether if there's more things happening, there's a broken window syndrome or something.
Yeah, I think those are great.
And people feel if it's not so important, right, or something like that.
Yeah, so I think that's a great question. I think that's beyond the scope of our analysis and my expertise of what's causing these delays. There are people who've looked at if I, for example, make reporting responses to reporting more visible, does that lead to downstream increases in reporting rates? I don't know of anything. I don't know of any way to compare these various causes of is it maybe trust in government or internet access or all sorts of other things. But yeah, no, I think there's definitely a bunch of causes that are good to study. Right, and so let's just contextualize this in terms of days. What our coefficients would suggest is a hazard, tree in poor condition, high risk, reporting delay of about 2.5 days in Manhattan, 4.7 days in Queens. Slightly less, less risky thing, tree damage, poor condition, but it's not about to fall on anyone, 15 days and 28 days respectively. And then a minor issue, these imply 112 days and 200 days. Right, okay. And so is the method actually correct? We made a whole bunch of assumptions in the modeling. What I'm showing you here is in some incidents, we actually know when they happened because they happened because of a storm, right? So Hurricane Ida comes in and knocks down thousands of trees in like a 3-hour period, right? And so any knockdown tree, any fallen tree that happens the week after, that's reported the week after Ida, you can probably guess that it happened because of Ida, right? Because of the hurricane. And so all you have to do is, so you know the reporting delay because you know when the hurricane like landed, you can read off a weather report, and then you can look at our model and get the estimated delay, and sort of like the averages line up nicely. Sort of the true delay, and on average ends up being slightly smaller than our estimated delay. You know, you can tell all sorts of stories about why that might be true. One is that like after like hurricanes, like everyone's in reporting mode, or like they're especially dangerous, even more than the covariates can explain. But you know, yeah. Okay. Any thoughts on this work or? Okay, so let me move on. So in this project, our goal was to measure reporting delays. Now, one thing that we can't do here is, well, can we estimate the ground truth, right? Like, how do we actually back out, like, right now, is there a flood in this street if it didn't report? And because like that's often, especially after emergencies, that's what you care about, right? Like what you care about is like emergency response of allocating resources to a bunch of areas. And if the only places that you can allocate are the places that have already reported damage, then you're probably skewing sort of socioeconomically where you're allocating response resources. And so in this next project, well, this is with PhD student Gabriel Agostini and Emma Pearson, who's another faculty member at Cornell Tech. The question is can we recover information about unseen events? And the key idea is you can use spatial correlation, right? So what's the spatial correlation idea is whether a street is flooded is correlated with whether its neighbors are flooded, right? So if every neighbor of my street reported a flood, but I didn't, I'm probably underreporting. If none of my neighbors report a flood and I also don't, well, it's probably because there isn't a flood here, right? And that's like, okay, that's like probably not true at very individual contexts, but certainly on average, sort of that idea is true, right? And whether the flood is reported, conditional on having occurred, will still allow it to vary by socioeconomic factors like we did before. So I'm not going to walk through the model and so on, but this lets us recover ground truth probabilistic estimates of where incidents have occurred after a flooding incident based on just the reporting data. All right, so this is a map of Hurricane Ida. You see the reports and the stripes, and then our model's estimates of actual flooding sort of around it. And then we can do similar sort of verifications using like future reports and so on, and sort of we know that our method sort of validate that the method directionally works. And then what's really interesting here is that then you can do counterfactual inspection allocation analysis, right? You can say, what if the agencies, and this is what they do, after storms, every agency is in emergency management mode. All they're doing is trying to figure out where the problems are and sending maintenance crews. And if what you do is, literally just inspect to where the things are reported, right? So here's the demographic mix of what you're going to inspect and work on. And if you use our model, sort of you get closer to demographic sort of parity of where you're inspecting and working on. And the reason you do that is because sort of the model is correcting for heterogeneous underreporting, right? The model is, I don't have that slide. The model is sort of learning that reporting correlates with socioeconomic factors, and it can undo that in its estimates of where incidents have occurred when it's taking advantage of the spatial correlation. Okay, great. Right, so far what I've talked about is a couple projects on, okay, how do we, what I motivated at the beginning is how does heterogeneous estimation of data yield different decisions or sort of potentially affect decisions at a high level? And how do we even understand whether that's happening, right? Like, how do we even understand that some neighborhoods are underreporting compared to other neighborhoods, right? But that leaves the actual, the last slide hinted at a decision-making aspect of allocation, but sort of there's a whole rich aspect of like, okay, how do I actually understand decisions and understand and improve decisions that's based on this data? And so one project that we're working on, or sort of a couple projects that we're working on now, is in this stage is how do we understand and make better decisions, right? So you have your response workers, both inspectors and maintenance crews, who are spatially distributed. And from a policy and individual worker perspective, what sort of the decisions that are happening are the number of workers in each location, right? The number of workers dedicated to each borough. And within each borough, within each worker, what incidents are they prioritizing? Are they prioritizing by risk and age, by like richness of the neighborhood? What are they actually doing to prioritize this? Right, because different policies here are going to yield different sort of delays in inspections and work orders. And so, and so what we're trying to do is we're trying to understand these policies using the observational data and then trying to sort of come up with better policies. And so I'll skip the actual projects here, but sort of in terms of understanding the policies, one project that we're doing is we're trying to cast it as a choice modeling estimation approach. So today or this hour, the agency had these 100 things they could have inspected, and here's the 50 that they did. Can we sort of understand the characteristics that are associated with their choice of which 50 they inspected? And then sort of the next thing we're working on is how do we actually set these policies, right? And you could imagine that different choices of these policies have different efficiency and equity sort of implications, right? So if you put everyone in Manhattan, that has different sort of efficiency and equity implications, however you want to measure that, than if you put the same number in each borough or put in proportion to your estimate of how many incidents there are, of how risky they are, and so on. Right? And potentially one thing that you might be worried about is that there's a huge efficiency equity trade-off. That like one choice here is like really good for making sure you get all the risky incidents immediately, but it yields to inequitable decisions in sort of which neighborhood are you leaving risky incidents on the ground longer. In practice, I don't have a plot here because sort of we're like pretty sure about the result, but not sure enough to put a plot that I want to commit to. So sort of in practice, what we're finding is that there's actually a particularly small trade-off, right? And especially compared to like how suboptimal the status quo is, right? And sort of the intuition for that is in a lot of these allocation, and I think this is actually extends in what we're also looking at in our congestion pricing work, is in practice, especially for allocation decisions, the efficient thing to do is often the equitable thing to do, right? So if what you're doing is leaving a bunch of high-risk incidents on the ground longer in one neighborhood, now that's certainly inequitable, right? That neighborhood is facing the brunt of the risk, but it's probably inefficient as well, right? Because you're leaving a bunch of high-risk incidents on the ground in that neighborhood. And you can like certainly construct examples where that's not true, right? You can certainly construct counterexamples where like, every incident in one neighborhood is like epsilon less risky than every incident in another neighborhood, and then like that incident, sort of then there would be a huge trade-off and so on. But sort of it turns out that in the regime that we're in, a lot of these settings, those examples are not what are emerging. Okay. And then finally, okay, so I think with my time, the ratio of service allocation to congestion pricing ended up being 100 to 0. But sort of I'll end here, which is we're working closely quite a bit with, right now, the Department of Parks and Recreation. We're trying to make headway with other agencies as well of like sort of translating the things that we're doing into like data dashboards that sort of, this was built by a star undergrad who worked with me last summer and is continuing to work with me, and Ahmed. Yeah, actually, I'll just end here.